Okay, good morning, good evening, everyone. Thank you very much, Jose, for that nice introduction and for the invitation to speak at ISQED. And as Jose mentioned, my talk is about the intersection of three areas: architecture, machine learning, and security. And really what makes this intersection interesting at this point is that we're an interesting time in terms of the evolution of computing in general and computer architecture and systems in particular, driven by the end of Moore's law, as well as the emergence of new computing models, which have forced upon us several trends, including specialization. So with Moore's law ending, one of the remaining ways of getting performance is to specialize architectures to important applications such as machine learning. Also, the cloud is becoming ubiquitous. So we're moving from this conventional computing model, or we've moved already from this conventional computing model where we think about, from a security perspective, protecting a system from the world because we are offloading our computation often. And as a result, perhaps we need to protect our data and our computation from other people that are running on the cloud, as well as the cloud provider themselves. Of course, machine learning is everywhere. I mean, you could see this even in terms of the push in both industry and academia to introduce machine learning into everything, and for good reasons, right? I mean, we're all excited about this new technology, and it seems to outperform ad hoc techniques, especially with the availability of data that is becoming, more abundant nowadays. And of course, there are perhaps less relevant to this talk. With the end of Moore's law, there is interest in sort of paradigm shift technologies such as quantum and DNA and 3D devices. And these sort of what we think of as exotic now will eventually make its way to be available through the cloud, and potentially, if it's successful, to basically end user devices over time. So my talk, as I mentioned, is at the intersection of these three areas. And I think we as a hardware EDA community, we've been spending increasing time at this intersection of hardware and architecture. For example, most of the previous talk was in this area, and it's along two different lines, right? So we think about leveraging machine learning and AI for architecture. So we have a lot of resource allocation decisions and other policies that we implement within systems, and we want these to be also benefiting increasingly from machine learning. But maybe the bigger trend in our community has been how do we build architectures to make machine learning more efficient. And I want to talk about basically this three-way intersection, right? So what is happening in terms of security, and what role does systems, or do systems have to play in terms of securing machine learning as it runs on systems? And to get to that point, I want to talk about the piecewise intersection of each of these two areas first. So as I mentioned already, we've been, as a community, spending a lot of time developing new architectures for machine learning. Both training and inference are expensive. So the data revolution and the machine learning revolution has been kind of enabled by our community, right? It's not just the presence of data or development of new machine learning algorithms. It was also the presence of GPUs and nowadays accelerators that makes all of this possible. And as we have more and more deployment, we're starting to get interested in new regimes. For example, IoT, as we saw in the previous talk, when we need real-time responses. So now you're thinking about machine learning under both power and time constraints. And that gives us a lot of work as a community to kind of come up with new designs that are innovative, that can meet the demands of these applications. So the picture here is an NPU, which is a neural processing unit, which is something that's embedded in high-end SoCs, high-end mobile devices nowadays. And on the right hand, this is a TPU. So you can think of an NPU as a TPU for mobile devices. Of course, the other place is, or the other kind of cross-pollination that happens is when we leverage machine learning to make architectures and systems better, right? So we see a lot of this happening both in terms of design time as well as during runtime, and also for security, for example. So, this is, these two kind of ways of cross-pollination between these two areas are important, and I want to argue later that they each bring sort of unique security concerns. On the other hand, when we think about the intersection of machine learning and security, this is also a very hot area. So the security of machine learning is obviously critical as we rely on it more and more. So how can we ensure that when we use these systems, they are secure, mostly that an attacker cannot get them to decide in their favor, and maybe in another dimension that an attacker cannot basically somehow from the behavior of these algorithms be able to infer something about either the data or the model. The model itself sometimes is kind of the secret sauce or the IP that a company owns. So we want to also be able to protect it. So I want to use this as an opportunity to discuss some of the threat models, some of the types of attacks that face AI. And of course, this is in general without, before starting to talk about how these are, what is the, when we add architectures and systems, how do these attacks become, more specialized to us as systems people? And also think about opportunities to mitigate them using the system. So, so that's basically security of ML. And of course, the other side, the cross-pollination happens both ways. ML is a very useful tool for security. So most obviously, when we talk about intrusion detection and anomaly detection and things like that, this is a data analysis problem, and machine learning can serve a big role there. So, so I want to introduce 3 threat models because I think they're kind of big, bags of attack types rather than a specific attack. And there are others, right? So I just want to use these as an example of the types of threats. So I think everybody here probably has seen and is familiar with adversarial attacks, where, for example, I have an image going into a classification model, and then an attacker has an opportunity to add usually human imperceptible noise. Of course, it's carefully crafted. It's not random noise. Random noise would not be able to achieve this goal. And then be able to kind of get this picture to be completely misclassified. And you can think about this as something. So if this machine learning system is on the critical path for a decision within a robot or an automated vehicle or something like that, misclassification can lead to fatal results potentially, right? And can cause the attacker to completely take over a system that is controlled by machine learning. And a version of this that is increasingly interesting is a real-time adversarial attack, where you don't construct this adversarial attack ahead of time, but rather as the attack is happening, or as the event is happening. In this case, this is a voice recognition system. So maybe I start listening to what a speaker is saying, and I'm able to predict the rest of it and inject adversarial noise at the same time, so that I can turn a yes into a no as far as the classifier is concerned, right? So get the system to do a decision, that the user did not intend. So adversarial attacks are one type of attack. Another type is membership inference attack, and this class of attacks is essentially focused on privacy. Am I able to figure out the data that was used in training a model? So the attack that Professor Han talked about with leakage from the gradients is an example of this type of attack. So we use private data to train a model, and now we think that allowing people to use this model does not expose information about this private data. But in reality, I can query this model, for example, multiple times, and based on the answers that I get, be able. So if this is an image that was used in the training, the confidence in the classification of the image. So essentially, the model is overfit for this image because it was part of the training input. So as a result, I can, from the model, infer information about the data and compromise potentially HIPAA protected data, or just kind of commercially valuable data, by being able to do this kind of attack. So this is another type of threat that is, that machine learning systems are vulnerable to, or I should say machine learning algorithms are vulnerable to. A third type of attack that I want to introduce, because we're going to use it in some of the subsequent work, is model extraction attack. So in this case, I've trained a model that I'm going to use on maybe a cloud resident service to classify something, right? Images, or you have these apps where you take a picture of a plant and it tells you what the plant is, or some service, something that that I'm using this model for. And of course, the idea is that this data is not, I don't want it to leak out to the world, and that's a previous attack. But also, I don't want the model to leak out, because then I lose my advantage where I have this, I have access to this data. That's the IP that I have. And if other people can just recover the model, then it's equivalent to them having access to my data. I lose my commercial advantage because of that. So the attacker can just query this model over and over and over again, and then use these responses to build a proxy model that can improve in accuracy the more that you could query it. So essentially, I can recover the internals of this secret model by having access to its API, right? So this is what a model extraction attack is. So either building a proxy model that is almost the same as the secret model, or actually more directly recover the internals, the hyperparameters of the network that is being used. Okay, so that's the intersection of ML and security. So the last piecewise intersection is the intersection of architecture and security, and this is what like my group spends most of their time doing. And of course, this includes two directions. One is vulnerabilities that are exposed by the architecture. So when we build a processor or an accelerator or a GPU or what have you, a lot of the time, for efficiency, we allow it to be shared between multiple potentially mistrusting processes. And as a result, they're able to use just regular software interfaces to mount attacks. And these include, if you've heard of them, covert and side channel attacks, where I use the contention behavior, for example, either timing or cache misses or performance counters, to infer information about the other application. And then these got leveraged into transient execution attacks or speculation attacks, such as Meltdown and Spectre, which have been in the news a lot. And of course, we have fault injection attacks, where I can drive a system outside of its operating parameters and cause it to experience an error. And then we add some, mathematical magic and some machine learning, and we're able to kind of infer information. So if the error happens in a cryptographic key, there's a lot of work out there that shows you could compromise encryption algorithms and recover keys quickly by doing that. And traditional fault injection required physical access to the device, but nowadays we have attacks that can be done from software. So of course, Rowhammer is the classical example, where I can cause bit slips in DRAM just by executing a particular set of instructions that repeatedly access adjacent rows. And Plundervault, if you've seen that paper from, I think, Usenix Security last year, where we use basically power control interfaces to undervolt something and cause it to experience errors. And of course, we have supply chain issues like hardware trojans and so on. Conversely, we can think about defenses that are rooted in architecture. And I think of those in two categories. One is this do no harm category, where these vulnerabilities that we basically introduce by building hardware that enables these kinds of attacks, we'll try to build hardware that does not expose these attacks, right? So build systems that are not vulnerable to these classical attacks on architecture. And then conversely, we can think about security as a computational problem. So a lot of security techniques and mechanisms like information flow tracking or control flow integrity and so on. A lot of software security techniques are really expensive to implement in software. So we can think about hardware acceleration, or essentially think of security as a workload and then build accelerators for security to help with that. Okay, so that's the three two-way intersections, and I want to introduce this the center of the Venn diagram using three examples that are specific attacks, but hopefully highlight a more general trend in each of them. So the first example, the trend is when we use machine learning within a computing system, does it become vulnerable to these attacks on machine learning? And then in retrospect, how do we build machine learning, robust machine learning to use within computing systems? And then I'm going to introduce the two other areas as we get to them. So this is the first example, and this is based on a paper we had in Micro in 2017. And in this case, the machine learning that we're using in a computing system actually happens to be related to security. So, hardware malware detectors are basically a machine learning technique that we use to embed detection for malware in hardware. And I'll show you that it's basically vulnerable to adversarial attacks. And then we have to think about how to build these detectors if we're going to use them in a way that avoids evasion. So the motivation for hardware malware detectors is that malware is exploding. And these are, I apologize, these are slightly outdated results. So every security company, at least virus scanning, companies with virus scanning products, keep track of something called their malware zoo. And this is just the samples of malware that is collected over time. And if you notice, the number of malwares is really, almost a billion different malware samples, and also the speed of their arrival. So over 350,000 malwares registered every day are both overwhelming. And as a result, if we want to build, static malware detectors, things that do signature matching like classical antivirus systems, every day there are new samples. And in fact, this is one of the drivers for why there are new samples, because we want to avoid detection as malware developers. So malware is obfuscated, it's packed, meaning encrypted and decrypted on demand, and it's recompiled several times a day. And this is what drives this explosion in the number of malwares. And it's there on mobile devices and on desktops and every platform that you can think about. So as a result, static analysis doesn't work. So the gold standard is something called dynamic analysis, where as the malware runs, we monitor its behavior. And no matter how obfuscated it is, the hypothesis is that the behavior cannot be obfuscated. So if I want to achieve something malicious, then I'm going to see this behavior as I operate dynamically, even if I hide it in the binary or whatever. So as a result, dynamic analysis is needed, but it's super expensive because it requires instrumenting my binary and monitoring it continuously. And as a result, it's just not done continuously. For example, to get a new app into the Google Play Store, there's a tool that they used to have called Bouncer that does dynamic analysis. People think for 5 minutes, and if your app doesn't do anything, malicious in 5 minutes, they say, okay, it's good. Let's let it into the Play Store, because we cannot afford to keep analyzing it all of the time. So HMDs developed as a response to this need. So again, the hypothesis with these guys is that malware is different from normal programs, and therefore we can detect it as a computational anomaly. So if we use low-level features to avoid instrumenting the program and analyzing it, So these are things like architectural features like branch targets or memory reference patterns or frequency of memory operations, I/O transactions, interrupts, mispredicted branches or cache hits and cache misses. So anything that's happening in this low-level space, in fact, we can even go to physical features. We can collect and see if it helps us in identifying malware from normal programs. And then if it works, then doing this classification in hardware is really cheap. So we can keep it running all the time and we get dynamic analysis, albeit at a low level, cheaply and continuously. And the idea is perhaps this will be a more noisy detector, but then we can provide this information to the expensive software detectors so that they can prioritize which processes to monitor. So this is an area that actually has received a lot of traction. Qualcomm advertises that there is something like this within their Snapdragon processor, although I'm not sure if it continues to be there. And this is an active research area in architecture and EDA conferences. So our paper in 2017 wanted to explore whether we can do adversarial attacks to evade detection. So every time we send a paper out on this topic, the reviewers rightly say, but are these strong features? If a malware developer was aware that you have a detector, would they be able to basically change their binary so that they can avoid detection? So we wanted, first of all, to explore this question. So we wanted to reverse engineer a detector. So if we didn't know what the detector looks like, are we able to reverse engineer it? And this is a type of a model extraction attack. So we query it over and over again, and we build a proxy model for it. And if we're accurate, then if we develop attacks on our proxy model, we can transfer them to the original model and they will work. And this will allow us to develop evasive malware. So we were able to show that we can reverse engineer and evade detection. And then the next question is, well, is this a fundamental flaw in these detectors? So if they can be evaded, does this mean that this technique is useless, that it's just really, a false sense of safety that we get? We tried to build hardware malware detectors that are robust to evasion. And this is the proposal that we had is this, resilient hardware malware detectors. And we can show that it's provably harder to reverse engineer. And as a result, you can't accurately get the model and you can't accurately develop transferable examples. So this type of attack, I'm going to get a little bit technical. If you don't get this, it's okay. It's called the black box attack. So I don't know the internals of your classifier. So our HMDs will not help with a white box attack, or at least we can't prove that they can help with it. Because so a white box attacker knows exactly the details of the classifier and then is able to generate attacks directly on that classifier. Okay, so let me quickly walk you through the attack. So the first step was to reverse engineer an unknown classifier, and we approached this as an optimization problem. So our hypothesis is, if we guess the parameters of the classifier correctly, then the proxy model that we build, the reverse engineered model that we build, will be more accurate. So what I mean is, we don't know, for example, the classification algorithm, whether this is a neural network or a logistic regression or some kind of DNN or a decision tree. So if we guess correctly, then our accuracy will be higher. So as a result, we keep reverse engineering candidate detectors, and where we get the optimal accuracy, this is most likely the internal model that we have over here. So given that if the space is exponentially large, then obviously we can't get the exact model, but we should be able to get something close to it. So we treat this as an optimization problem, and we're able to get something that is close to the internal model that is used on the system. And we can see that, so for example, we built classifiers based on instruction features, memory distribution features, and then architectural features. So these are cache hits, cache misses, and so on. So we are able to reverse engineer them with almost kind of 100% accuracy. So this tells us that the current generation of hardware malware detectors can be reverse engineered. So once we reverse engineer it, can we evade it? And the challenge that we had here was not a machine learning challenge. It was actually a security challenge or a malware challenge. As I mentioned, malware is a lot of the time encrypted. So this is called packed malware and obfuscated. So we can't just reverse engineer it and get the code and then modify the code to try evasion. So we had to come up with something that works, even if we can't reverse engineer the malware. So what we did is we construct dynamically the control flow graph of the malware. So as it runs, every time you see a branch, you say, okay, this is the end of a basic block, and then you start another basic block where it is. And then you build dynamically the control flow graph, essentially the the structure of the program that is running. And then we inject instructions chosen to evade our proxy model at the end of every basic block. So these instructions should not corrupt the state of the program, and they are selected to modify the features that our proxy model is using. And if our proxy model is accurate, then probably these are the features that the target detector is using. So we looked first at logistic regression-based detectors. These are hardware detectors, so often they don't use neural networks or something sophisticated because we want them to be both quick and low overhead. And we see that if you inject even a single instruction chosen carefully, so these are adversarial attacks, we can completely avoid detection. So of all the malware that we could detect before, even one instruction injected, 90% of them are no longer detectable. And if you inject more, then you end up with even more effective attacks. So the conclusion is sad, right? The blue bars here are if we inject a random instruction, and that has no effect on detection. But if we adversarially inject an instruction, then we can no longer detect the malware. So the conclusion is that the published HMDs at that time are vulnerable to this type of evasion. So these attacks are not difficult to build, and perhaps it's time to stop and say, is it worth it to do this detection? So we ended up thinking about a detector that would be immune to these types of attack, and this is now transitioning from showing that if we just use machine learning in systems, we can be vulnerable to attacks, to thinking about how do we build them robustly. So in this case, we built a set of diverse detectors. So these could be, different learning algorithms or different configurations. So the period of instructions that we look at before we do a decision, do we look at, do we collect a feature over 1,000 instructions or 10,000 instructions or whatever? And we build or we train a number of these detectors. And what we do is over a detection period, we're going to use one of them and then stochastically switch to another one. And the fact that we switch between them unpredictably, there is work in adversarial machine learning that shows that you can get a measurable advantage. So essentially a theoretical advantage in the accuracy of reverse engineering. And this advantage increases or proportionately to how often the individual detectors disagree. So if all the detectors are exactly the same, then of course you get no advantage if you're switching between them. They always produce the same output, so it doesn't matter to the reverse engineering. But if they're diverse, meaning sometimes they reach different conclusions, then you get a protection that is proportional to how often they disagree. So, so as a result, what you can show is basically if you have a diverse set of these guys, then an attacker that tries to reverse engineer them cannot reverse engineer them accurately, and as a result, they cannot mount the attack effectively. So here's an experiment with no attacks, and we have two detectors that we switch between, randomly, and they differ on the feature that they were trained on. And then three with three different features, and then we start varying both the features and the detection period. So in this kind of most protected case, we have 6 different baseline detectors. And there's almost no difference in, just detection during no attack. When we introduce an attack, then this is the attack with a single injected instruction. You can see with two features, we get some protection. So before we were dropping to like 10% detection, but it's not great. And as you increase the diversity and the number of the detectors, you get more and more robustness in how well you detect. With the configuration with 6 detectors, we pretty much were on par with the situation where there was no attack. And in fact, this does not change, this conclusion does not change that much when you kind of inject more, so that you allow more noise to be injected in the program. So as the intensity of the attack increases, you can see that we continue to detect attacks with high resilience. Okay, so that's my first example, which is the takeaway is be careful to use machine learning in any phase of actually systems, especially online, because then it's accessible to the attacker. And then if you want to use them, then you have to think about these attacks and build robustness in to make sure that your system cannot be subverted. The second example, I'm happy to take questions at any time, by the way. So I cannot see the chat box or if there are any raised hands. So I'm not sure what is the best way to interrupt me. So maybe you or Jose can let me know.
Yeah, I can see the whenever there is a raised hand or if there are any questions, but there are none at this moment.
Okay, all right, that's good. That's good. Actually, it's not good that there are no questions. Hopefully you have questions, but it's good that I didn't miss any of your questions. So the second example that I want to talk about is basically whether the architecture can be used as a way to attack machine learning systems. So this is based on a paper that we had in CCS 2018. And the goal of the paper was not necessarily basically attacking machine learning. It was one example that we used in the paper. The focus of the paper was to demonstrate that side channels are possible on graphical processing units. So side channels, I'm going to use this cartoon to give you an intuition of them. So you've seen this probably in a lot of movies where, the thieves sometimes are the heroes or the main characters in the movie, and they go in and they find the safe, and now they want to break in, and the safe is like so, well defended. You could shoot like a nuclear weapon on it and it would be still standing. But then somehow somebody comes in with the stethoscope and they listen to the mechanism as you turn it. And unintentionally, there is a clicking sound that comes up at certain points in the operation of the mechanism. And this sound, this unintended side effect, ends up being enough to completely subvert the protection that you have in the safe, right? Just because it clicks at these points, then I no longer have to guess among this massive space of potential sequence of numbers. I have some clue when I hit the right number. So side channel attacks are like this. Microarchitectural side channel attacks basically use the fact that when two applications share a resource, then the behavior of that resource as observed by one application can give me some insight into what is happening in the other application. Okay. So in this paper, we wanted to show that GPUs can be used as a vector for leaking information. And if you know, GPUs are programmed using two different computing stacks. One of them is for graphics, that's their primary purpose. So things like OpenGL and nowadays, web-based interfaces like web GPU and so on can be used to task your GPU. On the other hand, they're increasingly available as accelerators or general purpose processors. And then we can, use OpenCL or CUDA to program them. And on the cloud, especially if I'm using GPUs, I'm usually using either CUDA or OpenCL. And this is where workloads that might be of more interest to us reside, right? Such as machine learning and encryption and cryptocurrency and things like that. So our goal was to show whether it's possible to infer information about a victim coming either from the graphics side or from the compute side, and see what information is available at the time. So we found at least 3 APIs that can leak information. So there is an API that allows you to query the GPU to see how much physical memory is left there. And you can think of, if you keep querying it over time, then you can see this memory go up and down, which tells you something about other applications. So when they allocate memory, then you have less memory available. When they deallocate memory, you'll see that there is more physical memory available. Timing is another leakage source. So you could time the operation of certain take the time of how long an operation takes, and that will tell you something about perhaps the input to that operation. And finally, we found that actually the doors are wide open. So because GPUs are hard to debug, they have very rich performance counters, and these are generally available at user space. So we found a lot of information that leaks through performance counters. So I'm going to maybe skip over this stuff. So this is sort of reverse engineering to try to see how we can get 2 applications to co-reside, let's say, on a single symmetric multiprocessor. I'm sorry, simultaneous multiprocessor, I should say, SM within the GPU or across different SMs. And actually, the one interesting thing that I can tell you is that during reverse engineering, you cannot produce output from the graphics stack. So the only way to produce output was to encode it in the pixels that are being rendered. So we're actually encoding information in the image that we're producing, and then using the color of the pixel to figure out whether timing was short or long, for example. So we found out things such as how we can get 2 applications to co-reside, and then whether the GPU is actually used at the same time by multiple applications from the graphics side and from the compute side. So we did a number of applications. So one application, just to show you the effectiveness of this type of attack, was an application either from the graphics or from the compute side to spy on basically web browsing as it's happening. We did this in a number of ways, so including memory allocation. So if I'm querying the memory size that's available on a GPU, then I can figure out that Chrome, for example, is allocating events such as this for Google.com, whereas the time series looks completely different for Amazon and completely different for Facebook. And then based on this information, I can do basically classification to figure out what the user is doing on their browser, right? So this is called basically a web browse recovery attack or website fingerprinting attack, I'm sorry. Once I figure out that you're on Facebook, I can follow you because every page on Facebook that you click on also has this signature. And once you get to the place where you type your password, I can actually use the time. So the input boxes get rendered with a fixed frequency if there is no event. And if there's an event, then they get rendered at the point where the event happens. So by just figuring out the time that allocations happen, I can figure out immediately that your password has 6 characters, and I can do something called timing attack that relies on the fact that on a keyboard, it takes a different amount of time for your fingers to travel from one character to another. So this is a well-known attack in security to actually recover your password with high confidence. So anyway, so let's move this to machine learning. So our last example was to show that we can build this attack, in this case using performance counters, to recover a model as it's running on a cloud GPU. So I can query the performance counters, and based on the hyperparameters of the model that is running, I get a different signature of the performance counters, and then I'm able to use the signature to reverse engineer the internals of the model, figure out the number of layers, the number of neurons in each layer, and so on. So we did actually a quite rudimentary attack where we were just trying to recover the number of neurons during backpropagation during training, because it was one of several examples that we did. And you can see that you could recover this fairly accurately. But subsequent work, so there was the Deep Sniffer paper from ASPLOS last year that did complete recovery of a deep model. And the leaky DNN paper from DSN also last year did something similar. They use different vectors for leakage, but they demonstrate that we can do these side channel attacks and recover the internals of the model as it executes on our system. So that's my second example. So we can leverage architecture. So the architectural attacks that are a concern for other applications are also a concern when we are doing machine learning workloads, and they can be used to compromise secret information within these models. I know I'm hitting against the time, so I'll quickly talk about the third type of opportunity at this intersection between machine learning architecture and security. And this has to do with the fact that we can use the architecture to improve the security of machine learning. So this is more of a defensive approach. And this work is based on a paper that we have appearing in ASPLOS, I guess, next week. The idea is to leverage approximate computing to improve the robustness of machine learning against adversarial attacks. So defenses against adversarial attacks, if you remember, these are the attacks where the attacker has the opportunity to modify the input, inject some adversarial noise to cause it to misclassify. Defenses include things like data filtering and transformation. So as the data comes in, I might kind of perturb it a little bit to interfere with this adversarial noise. Or basically taking into account during training the fact that we could have adversarial attacks. So, for example, there are defenses such as defensive distillation that tries to reduce the size of the model while at the same time making it robust by essentially a lot of these adversarial attacks use the fact that there is a gradient to kind of walk to the boundary of the classification. So you could do defenses during training that try to obfuscate this gradient and make it harder to produce attacks. The problem is, once you develop defenses, people adapt, and you can show that a lot of these defenses can actually be, defeated by subsequent attacks. And this is probably true for our defense as well. But I wanted to introduce it as an example of what you can do in the architecture to secure machine learning systems. Within a CNN, so this is focused on CNNs and on inference, but we think the idea can apply, during training and on other learning structures. You do a lot of these convolution operations, right, where you apply math to part of your input and then use it to produce an output through basically a sequence of multiply-add operations. So what we did is we took, so suppose that you're building this using an accelerator, right? Or a CPU or something like that. So you have these multiplier circuits that are often built through a sequence of basically these adders and half adder cells. And then what we did is we took this half adder cell, full adder cell, and then we replaced it with something approximate. And then we used that to build the multiplier. So as you can see here, the approximation is actually fairly violent, right? So we pass one bit out as the sum, and we pass the other bit out as the carry. So if you look at the multiplier, it actually ends up introducing quite a bit of error. So this is the exact multiplier output, and you can see what the approximate multiplier produces. And this is the difference between them, and it's highly nonlinear, but it's input dependent. But it turns out, so I apologize that we use this only on fairly shallow networks. And the reason was basically it was very hard for us to do the adversarial attacks on the approximate circuits, right? Because we did not actually build an accelerator. So we were essentially doing the approximation in software. So we saw on these shallow networks that there is almost no difference in the accuracy during normal operation. So both for MNIST on Linux and for AlexNet, it's almost the same accuracy. So what we did is we take a CNN that is pre-trained, And then we replace these exact multipliers with the n-exact or the approximate multipliers. We do not do any retraining. And it's interesting why it continues to work with no retraining, right? So what class of approximations can allow you to just plug in the network as is? So in this gray box attack, we allow the attacker to generate an adversarial example using the exact circuit. So this is, they don't have access to our approximate circuit yet. And they generate the adversarial example, and then they try it on our approximate network. So all of this is the accuracy after the adversarial attack. And these are a number of different algorithms for producing adversarial attacks. So on the exact circuit, the attacks basically always are able to fool the classifier. And then when you deploy the approximate circuit, the attack does not transfer, right? And so far, this is not too interesting because it's not an adaptive attack and it's not a white box attack. So the attacker really just produces their attack on an exact network. And then when they try it on our approximate implementation, the attack doesn't work a lot of the time. So there is some built-in robustness that happens because of that. And when we looked at it more closely, we see that the approximate model actually has more confidence in its output. So this is the confidence that is produced at the output of the CNN. And we conjecture, I mean, we're still sort of digging into why this is happening, but we conjecture that the approximation in the multiplier is actually adding noise in a way that highlights the features and suppresses sort of less important features. So we end up with higher confidence because of that. When we try this on a white box attack, where the attacker actually generates the adversarial example using the approximate circuit. So in this case, they know the internals of of the circuit. So there is no question that they will be able to generate an adversarial example. The only question is how much noise they need to add in order to be able to generate it. So if they need to add more noise, that means it is sort of an inherently more robust design. And then, so the success rate will be, if you allow indefinite amount of noise, the success rate will be high. But if it's a lot of noise, then maybe a human can detect that an attack is happening, or even kind of an automated detector might have like more to work with in terms of the magnitude of the noise. So as you can see here, basically the approximate model, so this is just a sample of images from AlexNet, requires significantly more noise. This is measured by basically image metrics, right? So the mean square error and the PSNR. You can see that there is an advantage of something like 4 dB in the PSNR. So the injected noise to fool the approximate model has to be 4 dB higher for it to work. And as you can see, of course, because we're using approximate computing, the main reason to use it, or the classical use of approximate computing, is you end up saving on energy and delay, and the energy delay product is lower. So we get both a more robust design while at the same time being more efficient. So if this is true, this is our first foray into this. So we have to do a lot more to make sure that this works on deeper networks and that there aren't obvious adaptive attacks that bypass it. We've tried some. Then this is kind of a situation where you gain both in security and performance. So that's my third example, and I apologize, I'm a little bit over time. I just wanted to kind of leave you with the thought that there is a lot of interesting research at the intersection of not only ML and security, but the projection of that to architectures and systems. And I did that using the 3 examples that we saw. And I want to think of them as exemplars, as examples of something bigger, each of them. Right? The first one is when we're going to use ML in computing systems, we have to worry about attacks on that algorithm, such as adversarial attacks, and design classifiers that are robust against them, or at least don't make it so easy to bypass them. The other one is that, or the other class of work that I think is interesting, is that we can leverage microarchitectural attacks that we use to compromise other applications as attacks on machine learning. And then if we're aware of that, then we have to design our machine learning algorithms, and potentially with the help of the architecture, to try to make it harder to carry out these types of attacks. And finally, basically machine learning algorithms run on systems. And even though most of our community is focused on traditional uses of architecture solutions such as performance and power and delay, I believe there's an opportunity to also improve security and robustness using architectural designs. And I try to animate that by the use of approximate computing that happens to be something that improves the robustness against adversarial attacks. So I think there are many other areas for cross-pollination, and I'm happy to hear your thoughts about that and take any questions that you have. Thank you.
Thank you very much, Nael, for this very interesting talk.
Thank you, Jose.
The floor is open to questions. If anyone would like to make a question, please raise your hand or simply type it in the Q&A. In the meantime, I have also a question which is related to hardware in a way. Yeah, if you look, for instance, at today's systems or microcontrollers, they also include these secure elements. Yeah, or if you think about the ARM processors, that they have this trust zone and so. What do you think we need to enhance on top of that to make our architectures more secure, say, against these type of problems?
Yeah, I think that's a great question. And so one of the ways that architectures can help with security is to offer abstractions and models that are useful from a security perspective, like trust zone and SGX and similar systems. Now, it turns out that basically these help with isolation type attacks, right? So attacks like memory corruption and things like that, where we're able to escape from, let's say, a process isolation to be able to read something, or where a malicious kernel can read a process contents. But they don't really help with microarchitectural attacks. In fact, the threat model for trust zone and SGX, where you assume that the attacker controls the operating system, can actually make it easier to carry out, let's say, a side channel attack, because I can control exactly when one process runs and when another doesn't. So there is work on trying to come up with abstractions that are helpful against microarchitectural attacks, but they remain very much, in my opinion, research ideas. We don't have anything as mature and clean as trusted execution environments.
Okay. There is a bit more of time for questions and from the audience. No, I have another question. I was actually impressed by the number of malware attacks. I think you had something like 350,000 per day. It's huge. So what can we do really as a community against this? I never realized that was so many attacks.
Yeah, that's a great question. I think the attacks, I mean, luckily, maybe these are not original malware. So I think the samples are an example of the attackers trying to avoid detection. So malware now is an industry. So people make money out of it. So you have these botnets that are like shadow cloud computing systems, and then they sell access to the botnet so that you can carry, if you can send spam or carry a denial of service attack or something like that. So as a result, basically there's money involved, and the attackers want to protect their investment. And part of that is to make it hard to detect the malware. So every day, every piece of malware is repackaged and obfuscated and so on, which makes detection and security mechanisms harder and harder. So my takeaway is that we have to think about security as a workload. And just like we think about accelerating machine learning and accelerating, other important applications, we should invest as an architecture and EDA community in providing acceleration for software security techniques that makes it harder to subvert systems and attack them. Of course, it's a cat and mouse game, but you know, are we the cat or the mouse in that game? I'm not sure. So we as the cat, we have to continue to make it harder for systems to be attacked, and that's one of the ways, by investing in security in architecture and in the hardware.
Okay, I have two questions from the audience. First question is from Kevin Cameron. He says, is the SMP architecture intrinsically insecure?
Yeah, I think you're referring to, so with SMP, we have essentially two hardware threads that are running at the same time and sharing the front end of the processor. So things like the L1 cache and, you know, ports, there is this port contention attack and so on. So definitely it's more insecure because the sharing happens faster and at fine grain, and several cloud providers suggested turning off SMP as a way to basically make side channel attacks less of a threat. But the question is, can we design SMP in a way that exposes less of a threat? I think there is hope, but I wonder if we can do it without giving up the advantage, the performance advantage from SMP. And the problem goes beyond SMP because there are resources that are shared across cores, like the LLC and the memory ports and so on. So if we disable SMP, we might be more secure, but we're not secure against these types of attacks.
Okay, and second question is from Kitam Alatun, and he's asking, would verification help? And when do we do it for the architecture, before manufacturing or at running time?
Yeah, that's a great question. And I'm familiar with some people that have tried to do this using verification. The problem is, I think that the properties that you need statically to ensure, for example, that a shared piece of hardware cannot be used to leak information are extremely conservative. So there's several, hardware description language extensions for security that try to ensure non-interference and things like that. And it seems to devolve to either provide, so essentially partition or separate otherwise. So if you don't share, then you're not vulnerable, right? So this is kind of like turning off SMP. And I wonder if there are either like combined, static dynamic solutions that can do better than that. So you ensure some properties statically, and then dynamically, maybe you can, enable some sharing, given the weaker properties that are guaranteed through verification. I'm not sure. I think that's a very interesting, thread of research to explore.
Okay, with this, I would like to thank again Nael for his very interesting talk, and I close here the session for the tutorials. Thank you very much to all attendees, and enjoy the next session of ISQD. Thank you.
Thank you. Bye.
Bye.